Hello, this is Lab 5 by Zach Braun. This presentation will consist of a background, a problem, tracker, VPython, results, and conclusion. The background is that Anders Helstrup went skydiving 2 years ago in Norway, and he saw a rock plummet past him. He took it to experts, and he realized that they had captured a meteorite falling during its dark flight. This is when it has almost been slowed by atmospheric braking. Experts believe that the 20-kilogram rock that flew past Anders was part of a larger rock that exploded 20 kilometers above him. Anders passed this rock at 1,000 meters. The meteor was 50 meters from him. Experts believe that when the asteroid first entered the atmosphere, it was traveling at 19.16 kilometers per second. That's 19,160 meters per second. The problem is, was the meteor in terminal velocity when it passes the skydiver? The assumptions that were made is that a normal initial velocity for a meteorite about that size, the velocity of Anders is moving relative to the meteorite, and Anders' speed is much smaller than the meteorite, therefore his speed can be neglected. The size of the meteor on impact is the same as the size as it was while descending past 1,000 meters. I am also not taking account of the rotational momentum of the meteor. We are also not taking into account that Anders is moving because the meteor is only visible by him for 0.2 seconds. Anders was approximately traveling at 12.8524 meters per second. Although his speed is relatively close, he can barely see it for more than 0.2 of a second. I'll go over the fundamental principle. The fundamental principle that we're going to use is delta P equals F net delta T. And then we can separate that into PF minus PI equals F net delta T. Divide by the mass, and therefore get VF equals VI plus F net over M times delta T. We will work with this fundamental principle in the Python model. I decided to try something new and calculate the drag force. I learned the drag force equation in my aerospace class earlier this week. The equation is x equals m over b times v naught, where x is the penetration distance, m is the mass, b is what we're looking for, which is the drag force coefficient, and v naught is the initial velocity. X equals 1,000 meters, because that's when we first saw the meteor, and the mass of the meteor was 20 kilograms. We assume that this didn't change. I also calculated my v naught, which is my velocity initial, using the tracker video's first 2 frames, which we will get to later. After calculating the velocity initial and plugging in everything, I get a drag force coefficient of 1.167. This is my tracker video. I set my origin at the first point with the y-axis going down is negative, y-axis going up is positive, x going to the right is positive, x going to the left is negative. In the story I read about this video, the expert said that it only passed him for 0.2 of a second. Therefore, even though these are still frames, I had to set the time to 0.2 at the most. That is why there are 12, 16, 19, 22, 26. I had to set a high frame rate. Meteor was 24 centimeters in diameter. I used this as my calibration. I used the last point because that is where I could see it the clearest. Now watch my tracker video run. As you can see in the video, there is a slight deviation from the x. This is probably due to the rotation. Luckily for us, the motion in the x is independent of the motion in the y. Let's now talk about the forces that are in effect during this video. The weight force mg is going down. Drag force pointing up. If it's in terminal velocity, then they're about equal. In terminal velocity, then these two arrows are equal. If not, and the object is falling downwards, then the bottom arrow is greater than the top arrow. Let's now go over important parts of the Python code. The initial conditions is that the meteor, which I named ball, is 20 kilograms, and also that the position is negative 0.044.015. I got this from my tracker video. And then that also the initial velocity is negative 42.83 in the y direction. This is also from the tracker video. I also started the time at 0. So the drag coefficient, which is b equals 1.167. So I'm outputting my data to gravity and drag 5.csv. I want to know where the object is the whole time, so therefore I'm printing the position in my Python video. My calculation loop where t is less than 76.5. I came up with 76.5 by first plugging in a very big number, and I know that he's at 1,000 meters, and then because I'm printing the position, it tells me what it's landing at. So if the number was greater than 1,000, I lowered the time until I got to 76.5, where the meteor ends up at 1,000 meters. I then used the fundamental principle to calculate ball.vev and ball.p. This is what advances as the time goes on. I also calculated my weight force, which is negative ball.m times g times j hat, and my force of drag, which is b times the magnitude of ball.vev squared times j hat. And then the force net, which was evident from our free body diagram that we discussed earlier, is weight plus force of drag. I also made an arrow scale, which is 50, and then in the up, which is yellow, my arrow scale was the force of drag, and down was my weight. Here's the tracker versus Python model data. As you can see, this is very hard to understand because the tracker data is so small. The tracker data is so small because it only exists from 0 to 0.2 seconds, whereas the Python exists from 0 to 76. Because that was so small, I decided to model the velocity, which is the slope in the Python model. As you can see, it hits terminal velocity at around negative 12. It is also evident that it is at terminal velocity because the slope never increases once it hits the negative 12. The result is that the meteor does not reach terminal velocity until 3.5 seconds. This is 3.3 seconds after Anders witnesses the meteor. Therefore, when the meteor passes Anders, it is not in terminal velocity. The terminal velocity is negative 12.9983 meters per second at a position of 945.125 meters above the ground. The meteor impacts the ground with the terminal velocity of negative 12.9983 meters per second. Terminal velocity is when the velocity does not increase. That is why it has the same velocity at 3.5 seconds as it does at 76.5 seconds. Thank you for watching. This concludes Lab 5.